Calorimetry Part 1. Now, calorimetry is a process by which we can use experimental techniques to measure energetic changes in a substance through observable changes in temperature. This generally relies on the use of a calorimeter. A calorimeter is a device that allows the temperature measurements to be made through some sort of action or process on a known substance, which is generally pure water. If we know what substance is being affected by the system in question, and we know the specific heat capacity of that substance, we can measure temperature changes and relate them to overall heat. The change in internal energy of any substance will be equal to the change in the heat plus the change in the work. We must be able to calculate both the change in the heat and the change in work. Now, heat is a process that is measured by an energy change from a flow of high energy concentration to low energy concentration. If the internal energy of the system is not the same as the internal energy of the surroundings, then there will be a flow of energy until the energy of the system equals the energy of the surroundings. This is a process referred to as thermal equilibrium. This is the reason why if you have a hot cup of coffee and you let it sit around for a while, eventually it will get cold, because the temperature of the coffee will eventually equilibrate to the temperature of the surrounding air, because the energy that is in that hot coffee will be released into the air until it establishes a thermal equilibrium between the system, which is the coffee, and its surroundings, which is the air. The idea of an energy flow is an innate property of a system. Any specific energy change will be equal to the temperature change in proportion. So heat can be thought of as the change in the heat capacity times the temperature. So if we have a substance that has a heat capacity associated with it, which is C, that heat capacity times the change in temperature will equal the amount of heat that is either absorbed or released by the system. C is heat capacity, which is an extensive property. Heat capacity is specific to a particular sample. For instance, iron has a heat capacity that is dependent upon the amount of iron that we have. If I have a particular cast iron skillet that is, say, 9 inches in diameter, that cast iron skillet will have a different heat capacity from a cast iron skillet that is 12 inches in diameter. Specific heat capacity, or C sub S, is an intensive version of heat capacity. Specific heat capacity relates to the material the substance is made of. For instance, iron itself has a specific heat capacity that is intensive to that element. All iron has the same specific heat capacity, regardless of the amount of iron we have in the sample. Now, the heat capacity will differ, but the specific heat capacity will be the same. We can measure the absorption or release of heat such that the heat will be equal to the mass of the sample times its specific heat capacity times the change in temperature. Because the change in the internal energy of the system will be equal to the opposite of the change in the internal energy of the surroundings, similarly, the heat must be such that the change in the heat of the system will be equal to the opposite of the change in the heat of the surroundings. Because if the system is, say, releasing heat, then the surroundings will absorb the heat. If the system is absorbing the heat, then the surroundings will release the heat. So it's always the opposite sign. Work is applied energy. We can do many different types of work, but we will focus primarily on pressure volume work. We've defined work as being force applied across a distance, force times distance. If a gas is produced against constant pressure, expanding volume does work. Consuming gas at constant pressure will cause the volume to contract, and work will be done on the system. So if the system in the first case is producing gas, it is doing the work on its surroundings by expanding. If in the second case the gas is being consumed, the volume is contracting and the surroundings are doing work on the system. If we look at this example here, in the case on the left, if we have 3 moles of gas under a certain pressure being reduced to 2 moles of gas, then the overall volume will contract. Going from 3 moles to 2 moles, according to Avogadro's law, such that volume is related directly proportionally to number of moles, if numbers of moles decreases, then volume will decrease proportionally. As the system compresses, the surroundings exert force on that system. If work is force times distance, and pressure is force across area, we can rearrange pressure to solve for force such that force is equal to pressure times area. If we plug that in for force in our work equation, then work becomes pressure times area times distance. In a cylinder, the distance is the height of the cylinder because the area is the base of the cylinder. So pressure times area times distance can be the same as pressure times volume because height times area in a cylinder is the same as volume. Any change in work, then, is the constant pressure times the change in the volume. Now, the example that we looked at is a case in which work should be done on the system. If work is done on the system, then energy is being added to the system, which means that it's an endothermic process, and the value of the energy should be a positive value. However, the process of compression, where the final volume minus the initial volume is the change in volume, will produce a negative volume because the final volume is smaller than the initial volume. This means that when I plug in work being equal to pressure times the change in volume, my work will be negative rather than positive. We correct for this by changing the sign of W in the overall equation so that the final equation for work is negative pressure times the change in volume. Thus, a compression process which has a positive pressure and a change in volume that is negative will produce an overall positive value. An expansion process, which has a positive pressure and a positive change in volume, will produce an overall negative value because it is analogous to an exothermic process, where the system is doing work on its surroundings. We can substitute the W such that if we put that into our energy equation, which was change in energy is equal to Q plus W. If W is negative P delta V, then my change in internal energy becomes Q minus P delta V. We can relate this to the gas law such that W is equal to negative delta N RT. So in a case where we have a positive W, this occurs when the number of moles of gas is consumed. And it is negative when the number of moles of gas increases when moles are produced. As an example, what sign of work is predicted for each of the following equations? In this equation, there are no moles of gas on the left and 7 on the right. So 7 moles are produced and none are consumed. Thus, the change in the number of moles is 7 minus 0, or positive 7. Plugging that to our equation, we get a negative value. For this equation, there are 2 moles of gas on the left and 2 moles of gas on the right. 2 moles are thus produced and 2 consumed. Our change in number of moles is 2 minus 2, which is 0. Plugging that into the equation gives us a value of 0. Thus, no work is done. In this equation, there are 3 moles of gas on the left and 2 on the right. 2 moles of gas are produced while 3 are consumed. Our change in number of moles, then, is 2 minus 3, or negative 1. Plugging that into the equation gives us a positive value. Now, the change in internal energy for chemical reactions is a measure of Q and W. If we measure both Q and W, we can get the change in internal energy overall for a reaction. This is easier if there is no work involved. In other words, if the process occurs at a constant volume. So the change in energy is equal to Q minus P delta V. If the change in volume is 0, then that term is eliminated, meaning the internal energy change is equal to the heat. A bomb calorimeter is used for this kind of process. This consists of a steel container used to control the volume. Inside, the sample is contained in a large volume surrounded by a large volume of water, which absorbs the heat produced from the system. A high specific heat of the water causes a very small temperature change. which while maintaining a constant volume, makes it much easier to measure the internal energy. Because no work is done, all of the internal energy change comes from the actual heat factor of the equation. This is often used to calculate a heat of combustion, where I burn a substance. The heat is absorbed both by the water and the calorimeter. So we have to first determine what the amount of heat that is absorbed by the calorimeter is. We use a reference point, usually something like benzoic acid, which has a known heat of combustion of negative 3,227 kilojoules per mole. And this helps us to determine the amount of heat the calorimeter absorbs. We are able to calculate a calorimeter constant from this, where the heat of the calorimeter is equal to a calorimeter constant times the change in the temperature. The overall change in energy will be equal to the heat that the calorimeter absorbs plus the heat that the water absorbs. As an example, once we know that the calorimeter constant, we can solve for the heat of combustion, where the heat of the water plus the heat of the calorimeter is equal to the negative heat of the reaction. So if I have a 1 gram sample of ethanol that is combusted in a bomb calorimeter with a heat capacity of 2.71 kilojoules per degree Celsius, the temperature of 3,000 grams of water rose from 24.284 degrees Celsius to 26.225 degrees Celsius. What was the change in energy of the reaction? The change in temperature is a 26.225 minus 24.284, or 1.941 degrees Celsius. The heat of the water is 1.941 degrees Celsius, the change in temperature, times the specific heat capacity of water at 4.184 joules per gram degree Celsius, times the mass of the water, which gives us 2.436 times 10 to the 4 joules, or 24.36 kilojoules. The heat absorbed by the calorimeter is 2.71 kilojoules per degree Celsius, times 1.941 degrees Celsius temperature change, or 5.26 kilojoules overall. So the heat of the water plus the calorimeter is the 24.36 plus the 5.26, or 29.62 kilojoules. The heat of the reaction is the negative of this, thus negative 29.62 kilojoules per gram, because there was 1 gram sample. The change in internal energy is usually measured in mole terms, so we convert to moles by multiplying our 29.62 kilojoules per gram by the molar mass of 46.07 grams per mole, which gives us negative 1,365 kilojoules per mole as the heat of combustion.